Any time now, you should have it.
Yep.
Okay. Let me get back to the pictures. Got it. And welcome everybody to the Santa Barbara Astronomical Unit club meeting for September 2nd. These are on the last or the first Friday of every month. We have a couple of wonderful speakers for you tonight, which the Vice President will introduce shortly. We'll skip the business meeting parts because we have a separate meeting for that. And we'll go right to the one announcement that we have, and that is outreach.
Okay, outreach. Things are quieting down a little, but schools are going to start ramping up. Tomorrow is Kachuma Lake. Sunday is Refugio State Beach. Tuesday, first Tuesday, Telescope Tuesday at Community Rail Marketplace. And then on the 10th, the second Saturday, as always, it's the Museum of Natural History Star Party. And that's starting at 8. So we'll have the planning meeting at 6 and set up at 7. And then the third Friday of every month, the 16th, Westmont Public Telescope Night. 17th, Saturday, Carpinteria State Beach. There's also an event at Los Flores Ranch Park in Santa Maria that has fairly dark skies that some people may want to go to, but I'm going to be doing Carp State Beach. And then Saturday the 24th, once again, Carpinteria State Beach. And that's in the kind of in the middle of CalStar, which starts on the 22nd and goes till the 25th up at Lake San Antonio for those who are doing dark sky observing. So that's it for September, pretty much.
Okay, thank you. Karen, you're on.
Did you say I'm on?
Yes.
Well, okay. Mike Hardwick, I hope you're watching. You said you would be. You got YouTube running, 20-second delay, but everybody's watching. And don't forget, Monday morning, we're about to do our 80th program of the SBAU Astro Hour, also watchable from 11 o'clock on YouTube. I'm Ron Heron, the Vice President, and it's going to be a very special treat tonight, ladies and gentlemen. We're all seeing those great photos that are coming back down, distant planets and stars and galaxies downloaded from our latest super miraculous space telescope that NASA launched, I think it was back last Christmas, wasn't it? To its Lagrange point, 1 million miles out. We thought it might make an awesome presentation, members and fellow board members, for our beloved Astronomy Programs Director for the Museum of Natural History, and our new postdoc friend from UCSB and now Caltech, to give us a combined grand tour of the JWST, because there's plenty coming back. Krissie will do the first part, followed by Dr. Rocio, and I got a feeling we're going to see some amazing, great photographs. Dr. Rocio Kiman comes from Argentina, where she did her undergraduate studies at the University of Buenos Aires, moved to the States to get her PhD at the City University of New York and the American Museum of Natural History back there. Her specialty in astronomy is low mass stars, less than half the size of our sun. Brown dwarfs, for example, and someday we're going to have her on just for the hour and a half to talk about that. Frankly, it's about time somebody in astrophysics should stick up for the little guys in space, you know, those runts of the universe. A year ago, Rocio took a postdoc position at the Kavi. Is that what it is?
Kavli.
K-A-V-I or L? I can't remember.
L-I, K-A-V-L-I.
Oh, Kavli. I left out the L. All right, Kavli Institute for Theoretical Physics on the campus of our beautiful local university. This past week, she began another postdoc down at Caltech, where our last young man, Vice President Adrian Lopez, is now on a scholarship. And Adrian's having a good time. Krissie now is going to start things out. She's not only a longtime member and a big supporter of SBAU, but Krissie Cook is a NASA solar ambassador. Maybe that's ambassadress, but I don't think so. We say actor for both men and women, so why not ambassador? And the Astronomy Programs Specialist for our Santa Barbara Museum of Natural History. She also serves proudly as an advisor for our local chapter of the Girl Scout Astronomy Club. When not scanning the heavens, she loves going to the beach with her genius husband and 3 precocious but precious little ones. Very special program, ladies and gentlemen. We call it Krissie and Dr. Rocio's grand tour of the James Webb up to now. Krissie Cook, it's up to you. You have the floor. Hi.
Fantastic. Thanks, Ron. Thanks, AU. Thanks to everybody who's watching. Usually I watch the chat on YouTube, so I know those regulars that are tuned in. Hi, everybody. Please do, if you have questions, submit them on the YouTube chat, and someone will be monitoring and making sure I get that word. I do want to let you know, if you want more James Webb experts after this, the museum is hosting yet another expert panel this coming Friday, 1 week from today, September 9th at 4 p.m. That will be in the planetarium, comfy seats, air conditioning, for about an hour. It'll last from 4 till about 5, and that's free with museum admission, open to anyone who wants to come to the museum at that time. All right, let me just go ahead and share my screen here. And let's see. Good. Is everybody seeing that?
Yes.
Fantastic. Good. I want to whip through these first few slides because I have so much I want to tell you. As I was preparing this presentation, more and more new images and videos and information kept being released, and I just was like, I gotta put that, I gotta put this, and what about this? This is so cool. I can't leave this out. It's all just so amazing. So I'm gonna do my best to not talk too fast, but also share about 1,000 and million things and keep it all in less than half an hour, because I know you want to get to the really good speaker, Rocio. She is fantastic, and you're going to love her talk, and I can't wait to hear it. So I'll try not to go too quickly, but also there's so much I want to say. Oh, also, look at my awesome James Webb Space t-shirt. Okay, good. All right, let's get going. Just real quick, and actually Ron already talked about some of these different things, but here's a quick overview of the telescope itself. The top side, of course, facing away from the sun side, has this gigantic primary mirror, 6.5 meters in diameter. And then we have these sun shields, because these instruments are so sensitive, even the reflected light from, oh, hey, Sean Kelly. The reflected light from the moon would be enough heat to basically block out anything that we would see. So we got to make sure we're blocking all that heat from the sun, all that light. So there's those 5 shields. Okay, moving on. It's really big. It's so much bigger than Hubble. It would not be an exaggeration to say it's about 100 times better between the much larger primary mirror and the much more sensitive equipment. So we're getting way more data. By the way, here's our human person, right, for perspective there. The Hubble's primary mirror is about 6.5 meters. Excuse me, that's the Webb. The Hubble is about 2.4 meters in diameter. So much, much, much larger. Where is it? As we talked about, it's at L2. It's not orbiting the Earth. The Hubble Space Telescope's orbiting Earth. Webb does not. It's orbiting the sun out past Earth. And again, there's a side that is always facing the sun where those solar shields are, and there's a side that's always facing away doing the sensing. Okay, here's what's special about James Webb. It's looking at things in infrared light. What's infrared? Why do we want to do it? It teaches us different things than visible wavelengths would. Here are a couple examples, right? So if we look at these 2 creatures that you might see at a zoo, we can learn some things about them by looking at them in visible wavelengths. For example, meerkats have fur. This crocodile has scales. But in the infrared, we see that these meerkats have a really high metabolism. We can't tell that by looking at them in visible wavelengths. Infrared reveals that. When we look at this crocodile, we can see the crocodile, although crocodiles are cold-blooded as reptiles, this one is slightly warmer than the water around it, so it's probably been sunning itself recently. So it's almost like it's telling us more of its story by looking at it in the infrared. So if we look at the entire electromagnetic spectrum, we have all these wavelengths. Hubble looked at some visible wavelengths and a little bit of infrared. The Spitzer Space Telescope, which was recently decommissioned, also looked at infrared, but it was pretty old. It wasn't as sensitive. The equipment wasn't as good. The mirror was much smaller. So the James Webb Space Telescope is looking at a very wide swath of infrared. Now here is another reason we want to be looking at infrared, and that's because as we're looking at really distant objects, what was once a visible wavelength gets stretched out to a redder and redder wavelength. We'll talk more about that, but just, you know, basics. One more quick graphic. I don't want to go into too much because I want to get to all the pretty pictures. Hey, Tim. Hey, Chuck. But looking at these, you can, in this left-hand side of the image shows you that if we're looking at things that, you know, are closer, we have a shorter wavelength. As they get further, the same wavelength is longer as light is expanding through space. And on the right-hand side, this was really an interesting graphic to me, looking at this sort of like, here is as far into the past as Hubble can see. Webb looks way further. Look at that. Pretty exciting graphic. So what do we mean when we're talking about looking into the past? And again, for many of you in the know in the club, this is old hat, but just in case there's people who are learning about this for the very first time, I just want to touch on it really quickly so you can understand the science of how JWST is studying the sky. So if you have a star, here's our star here, it is giving light, and as it goes through, you know, in this case, a telescope, there's, if you imagine like a prism, it breaks up white light into all the colors, a rainbow as it were. So here's our continuous spectrum if you were to image this directly. However, when all that light passes through something like this gas, or even just like the outer gas atmosphere of the star itself, you're going to get places where these different gases either absorb, in this case, they're absorbing some of these wavelengths of light, or they kind of bounce out, and the ones that were absorbing it, they emit. So if it's like a direct view straight through, that's an absorption spectrum, and an emission spectrum, you can see they're like two sides of the same coin, right? They're like opposites. Hey, Dave Williams. So the Hubble Space Telescope is doing this. It's imaging these stars, it's breaking up the light, and as it does that, it's seeing these spectra. A spectrum is essentially like a chemical fingerprint. So for example, here's some spectra of different elements. Again, you can see exactly that flip side of absorption versus emission, but for sodium at these different wavelengths here, about what is that, like 410 nanometers? And then again, so if you saw this pattern, you'd know that this was, there's sodium, that it's, sodium is being absorbed here. Sodium is absorbing these wavelengths, I should say. Nitrogen is absorbing these wavelengths, hydrogen, and then oxygen, and so forth. Then we can combine this even further, and I don't want to talk too much about exoplanets because this is Rocio's thing, and I can't wait to hear from her. But we can then combine that to see how different molecules also interact as they are absorbed or emitted. Essentially, we're looking at light that is being blocked. So we're seeing, as we look at different atmospheres, for example, if we were to look at the Earth's atmosphere, which the James Webb will never do, it's facing away from the Earth, it's never going to look at Earth, but if it did, it would see that light being blocked includes a lot of CO2, some methane, ozone, carbon dioxide, liquid water, lots of liquid water. We can get all that just by looking at these spectra. Now, here's the next little piece of this puzzle. We're looking at all these spectra from all these different stars, but we're not looking at a static universe. The universe is changing, and of course, we all know the universe is expanding at an accelerating rate. And we know this because as we look at these spectra, we see this interesting thing. We call it redshift or blue shift. So we, the observer in this image, we're at the, let's see, are we at the bottom of the screen? I think we're at the bottom of the screen. Yeah, nope, we're at the top of the screen. Just kidding. Because, nope, we're at the bottom. Here's our light. Anyway, as this star is moving towards, in this case, it's moving away. We're at the bottom of the screen. It's moving away. Here's my mouse. My mouse is us. We're seeing these spectral lines, but they seem to shift as the distance from the star to us, the observer at the bottom of the frame, changes. It's moving towards us. We see these absorption lines shift to the blue. As the star moves away from us, we see it shift to the red. We do this for detecting exoplanets, but also we can do it for looking at stars or even galaxies. As we look at them, we see these spectra, and we can tell by how shifted they are how far away that object is.
Krissie, we can see that even if it's not transiting the star, with starlight coming through that atmosphere?
So in this case, we're kind of seeing it at like a 90-degree angle to the observer. We would see, like, if we are also along the same plane down here at the bottom, we would see this, the sun's distance moving to us here as shorter. Yeah, if we were seeing it edge on like this, we would just, it would be equidistant if we were looking at it from like out at your computer screen.
Okay.
Ron, this is the light from the star. It has nothing to do with the planet, but it's just showing that the planet is making the star move.
Oh, I'm sorry. I thought it was they were doing the atmosphere of the planet. All right, got it.
So this is just a general idea to explain how we see these spectra shift as things move towards or away from us. And of course, what's interesting is that pretty much everything in the universe is moving away from us. That's how we know that the universe is expanding. Everything is redshifted. Just depends on how much it is redshifted. So now let's get to the pretty pictures. I promised you pretty pictures and I want to deliver. Okay, so this was the very first image released by the James Webb Space Telescope SMAX 0723. And this one is a doozy. In this frame, we are looking at a point in the sky that is so small, be the size of a grain of sand held out at arm's length, where from Earth we basically see nothing. And when we look with the James Webb Space Telescope, we see this incredibly rich field. So there are a few things in here that are stars, and you can always tell you're seeing a star that's from the James Webb Space Telescope because it has this, they're called diffraction spikes. It's a pattern of these spiky things coming off, as you can see. These 6 hexagonal spikes, these are caused by the hexagonal shape of the mirror, and then the struts that hold the secondary mirror in place lead to another set of these smaller 1, 2, 3. There's like you can't see it's lined up with the other, but anyway, there's a pattern of 6 and a pattern of 3 diffraction spikes to make 8 spikes all together.
Chrissy, could you answer a question real quick?
Love to.
Did they use the exact same little pinprick place that Hubble used for its deep field so they can compare the two?
I'm so glad you asked. Can we wait to the next frame to answer that?
I'm sorry, I jumped the gun, didn't I?
It's okay. It helps me feel like I definitely planned this presentation on the right track. So I just want to point out that what we're seeing in the field here, this is a star, this is a star, this is a star, anything with these diffraction spikes is a star. So there's, like a dozen stars in the field. Everything else you see is a galaxy, hundreds of billions of stars, hundreds of billions in every one of these tiny specks. The big specks right here, the teeny tiny specks, the ones that are so small, they're just like a pixel on your screen. Those represent each one, hundreds of billions of stars. This is mind-bogglingly awesome. Not only that, but you can see what's called gravitational lensing. And gravitational lensing is when the gravity of something, Sean, you can't even see, I can't see a grain of sand in front of my face. I have to wear the right glasses. Anyway, we can see in this frame that the force of gravity from a galactic cluster in the foreground, and we know it's in the foreground because we've looked at the redshift, and there's some galaxies at the front here that are redshifted less, and there's some in the background that redshifted more. But these ones that are behind, the light from them is getting twisted and warped. A really great example is this particular galaxy right here. There's no galaxy that actually naturally has this weird shape, right? This is not how galaxies look. But if there's something really massive between that galaxy and us, that light gets shifted and warped and bent sort of like a funhouse mirror. And you can see all these weird circular sort of patterns around here. It almost looks like someone sort of spirographed the image that lets us know that there's some really strong gravitational forces at work. Okay, so Ron, you asked, what about Hubble versus James Webb? So here's that same spot in the sky as seen by Hubble, and then we'll see the James Webb version.
Got it. This is Hubble.
And now this is James Webb. Hubble. See how much less we're seeing? And then so much more. Next slide. Okay, let's see. Moving on, just again to talk more about this super incredible image. I mean, I just want to look at it again for another second or two. It's so pretty. It's so incredible. And this is a combination of 2 images. One was taken by, and I'll put both of them up, the mid-infrared, the MIRI cam. That's this one here on the left. And then the near infrared, the NIRI cam. So there's the MIRI and the near cam. These are 2 different infrared sensors on the JWST. And so they're looking at slightly different wavelengths. The wavelength numbers are indicated here below. But they're showing us different data, as you can see.
Hmm.
And they combine them for an image. Now, again, we were talking about like, how do we know how far away these are? Here's another really great example. Here are some different galaxies in this image. So here's this little, this is an inset here of this teeny tiny little, literally it's a speck, right? It's a speck. Here it is, and we can see these spectra, these fingerprints from different elements. There's hydrogen, oxygen, hydrogen. These are, you know, obviously going to be in galaxies, and we see them here on the spectrum, on our, you know, looking at our EM wavelengths. Here is one that's another galaxy, another just tiny speck, and this has the same fingerprint, the same pattern, right? Hydrogen, oxygen, hydrogen, but it's shifted to the red, so we know it's further away. Then we're looking at this little guy right here, which again is inset from a teeny speck. I can't even see on my screen. Maybe you can. Sean Kelly, I bet you can't. You make me feel better. This one is shifted so far, we still just see the hydrogen and oxygen without that other hydrogen pattern, but we know it's there. It's, you know, the same pattern. We can see it's exactly the same. So we know this is now, we're looking at something 13 billion light years away. So that light is 13 billion years old. That's how far it's redshifted. And then pushing the boundaries of the sensors of how far into the infrared the JWST can see this little buddy right here, this galaxy, 13.1 billion years is how long that light has been traveling at the speed of light through the universe constantly for 13.1 billion years. Now, we estimate the universe is 13.7, 13.8 or so billion years old. So these are some of the earlier galaxies in our universe. The Hubble Space Telescope could see to about 12.5 billion light years back. So we're seeing significantly further back in time, as it were. I know it's strange to say we're seeing through time, but that's essentially what's happening. We're seeing this light that's been traveling at a constant speed, but it's been shifted. And so if your camera can only see wavelengths to this line, if it can't see anything past this, right? If this is where Hubble can see something, great, we can see anything here, but we can't see anything past that 12.5 billion years mark, right? So to see anything that's older, we have to see further into the infrared. We have to see those waves stretched out even more, redder than red, sometimes they say. So that's just a quick overview of that. I want to keep it going because, gosh, I have so many more pretty pictures. Oh, I want to talk a ton about this, but I'm not going to for very long because there's so many other things I want to show you, but this is really cool. This is Stephan's quintet. These are 5 galaxies. 4 of them are traveling through space together. These 1, 2, 3, 4 on the right are all traveling together. And this one is actually just kind of hanging out in the foreground. It's like walking through the frame as we're studying these 4. These 2 galaxies are in the process of colliding. So that's how you see this really interesting interaction between them. And again, just a few stars in this frame, mostly galaxies. We'll definitely be looking at Stephan's quintet this winter and fall at our star parties. It won't quite look like this. We don't have the James Webb Space Telescope, so lower your expectations, perhaps. Oh, Tess is asking, is redshift only infrared? No. Redshift can shift even further, definitely.
Into radio waves?
Yeah, as far as I know. I mean, chime in if I'm wrong, experts, but you know, the further light is traveling, the more it's going to get stretched.
Okay.
And
so
Tessa, this is in general for things that you can see through your telescope, a very small effect. So you're not going to notice a star changing color because of its distance or its motion.
Perfect,
Also, you have the observed microwave background from early in the universe history, from farther back than JWST can see. And that stuff is all shifted down to the microwave, past the infrared.
Well,
right.
Did it take the James Webb to find these 5? Have we never seen this group of 5 before?
Oh, no, we've definitely seen these before. Yeah, you could see them if you have a nice clear sky and a decent telescope.
Oh, okay. So
they were named for a French astronomer who named them back in the 1800s, almost 1877. Yeah, it's in the constellation Pegasus, so out in the fall sky.
Got it.
Okay, so, oh wait, I see one more message coming in on chat. Oh, from Sean. Yes, Tessa, the stars in the Milky Way are not really moving relative to us, so the color is based on the surface temperature of the star. Yeah. Yeah, so the color of the stars that we're seeing is not because of like a red shift, blue shift. It's because of their temperatures within our galaxy, like our neighbors that we're looking at. Yeah, most of what we see in these deep field images, these are other galaxies, but when we're looking in our night sky, we're not really generally, especially not with our own eyes, we're not seeing other galaxies. We're seeing stars in our galaxy. But speaking of things in our galaxy, the Southern Ring Nebula, ooh, so pretty. And again, you can see the two different cameras with the two different wavelengths sort of give you complementary images, right? Like this one, we can see these outer layers really well in the near infrared, this warm dust. Then as we peer through here in the mid infrared, you can make out that this is actually a binary star system. This is the one that died, that, you know, burped out all this dust and gas. Something pretty similar will happen to our sun at the end of its life cycle. And here is something super cool that just came out this week. NASA has translated this into sound. And the reason they explained that they did this was to help people who are visually impaired experience and enjoy this data in a way that, you know, would be accessible to people who can't see. So I think that's pretty exciting. Oh, we have a question coming through in the chat. Why is the mid-infrared able to pick out the binary star? It's seeing through dust a little bit better. It's less obscured by all the other stuff in the way. So anyway, they've sonified, it's called sonification, these images. So I want to play you this video. Again, this is not sound coming from space. I want to be really clear. The James Webb Space Telescope is not like listening to space with a microphone. No, scientists and musicians worked together on this, and they took the data from the James Webb, which again, we can't say, we're already doing this in a different way, right? We're taking infrared and we're changing it into pretty pictures we can see. We're saying, we're gonna make these wavelengths look like red, and these ones will look like yellow, and these ones will look like blue, and these ones will look like purple. We're already extrapolating that data to make something we can't see, something that's invisible to our eyes, into something visible we can study. In this case, they've taken something invisible, this data, and they've transferred it into different sounds. So again, not how space sounds, but an interesting way to understand this data. So turn on your speakers. If you have headphones, this is a really great chance to like, listen in nicely to this one.
That's 2000 Space Odyssey stuff, my God.
And you can see that.
Yeah.
What's that?
Oh, it sounds like that, doesn't it?
It kind of does. Yeah. So they have a whole bunch of these, and they're kind of interesting. Let's see. We already did this one. They did it also for this really spectacular image of the Carina Nebula. This is a place where stars are being born. It's a stellar nursery with, you can see these bright, just formed stars and a bunch of just coming together tiny baby stars, just like, just littering the image with their incredible coolness. And so they have sonified this one in several different ways. The first way we're going to hear it is first just the stars themselves, where they just give a sound to the star, and then the lower part of the frame here, just this dust cloud, and then the background, and then they put it all together for us. So that's kind of interesting. Let's see what we have. Okay, so here we go. Just the stars.
Twinkle, twinkle, little star. Wow.
All right. Oh, Sean Kelly says, great movie sounds. Tim Crawford suggests, if we play it backwards, will it be a Beatles song?
You could probably integrate it into the Four Seasons, or actually the planets, not the Four Seasons. Who did the planet? Yeah, what was that guy's name?
Gustav Holst.
Yeah.
That's his name. I mean, ask a music teacher, right?
Yep.
Okay, so here are what they call this the cosmic cliffs. So this would be like mountains. They're not actually cliffs or mountains. They're gigantic, huge plumes of dust and gas coming together to form stars through nuclear fusion. But sure, we'll call them cliffs and mountains. Anyway, here's the way that they've interpreted this visual data into sound. And then here we have the background. Oops, I think I went one too far. Let's see. Take it on back. Oh, yeah. Let's see. We just hit this. Oh, this is the everything. Hold on. Give me just a second. This is the one I lost it. I lost it. Okay.
Oh.
Hold on. I've got it. Here we go. They all look the same in my preview panel. And you'll hear it panning from left to right. Again, as a cue for visually impaired people that this is where we're looking.
Now, how do they get that?
So if we put it all together, this is everything. Pretty fantastic. I really like that. Let's see. A couple more things. I'm just going to try and zoom through this. We're not going to do the zoom in, but the Cartwheel Nebula, galaxy, excuse me, super cool. Named not because it looks like it's doing cartwheels, but because this looks like the wheel of a cart, right? This is a place where two galaxies collided pretty recently. And so we have a lot of old stars here and new stars here at the outside. And these look like spokes on a wheel. We got to keep moving. Because, gosh, I have so many things I want to show you. Oh, this is a pretty cool one. This is that same galaxy, but just using the near cam, which again gives us a sort of a different view and helps us highlight other things. Other things that have been released recently. Oh, these cool images of Jupiter. Wow. These are so cool. The detail in those outer cloud layers. Gosh, I wish it looked this amazing when we saw it at our star party. It looked great at our star parties. Don't worry, Jupiter will be fantastic this fall. Somebody's asking what instruments are being used. That's a great question. They didn't say. They sound pretty electronic to me. Those stars were like little harp sounds. I'm not sure exactly what instruments they chose. But getting back to Jupiter, wow, you can see the great red spot. You can see that it's really bright, which in this image translates to higher elevation haze in Jupiter's atmosphere. These lighter areas are higher elevation haze. And then where it's really dark, that's lower elevation. You can see auroras on the northern southern poles of Jupiter, which is super cool. And then here's another further out image where we can actually see Oh, well, here's the annotated version. Jupiter's rings, pretty exciting. 2 of its moons, Amalthea and Adrastea, excuse me. And again, those auroras, pretty fantastic. The moons of Jupiter are extremely thin. They're almost invisible. But from here with the James Webb, what it's seeing is not necessarily, it's seeing essentially the heat from the sun reflected off these teeny tiny particles.
Wow.
So again, we have a hard time seeing that from Earth, but we see it here. It was a smaller galaxy punching through the larger one. Yes, Sean. Yeah.
I was going to ask, if you don't mind, why is that, except for the poles, a black and white version of Jupiter? Everyone I've ever seen, it's colors galore. Do they color?
Oh, yeah. Well, because this is looking in infrared wavelengths, so it's not showing us its true color. It's showing us different information, different data. Sort of like when we saw those meerkats and crocodiles, and they didn't look the same color. Yeah, these images aren't the same color. Jupiter's not going to look the same in infrared because we're not looking at visible wavelengths. We're looking in infrared.
Well, except that the poles are green. Isn't that the other end of the spectrum?
So those poles have like a ton of energy because they're interacting. There's an aurora happening where the solar wind is interacting with the magnetosphere of Jupiter.
Okay.
That's what that's showing there. It's not, again, it's not like a visible color, although sometimes you can see auroras and visible wavelengths on Jupiter and Saturn. All the gas giants occasionally.
Well, you'd think it could give us the real color of the big spot. That's red.
I mean, well, we have other telescopes that do that. The Juno spacecraft has been sending back incredible visual data.
Okay.
Yeah, so we could use different telescopes for that.
Got it.
Yeah.
And the Webb actually could see its ring.
Yeah.
Wow.
I know. Here's another image, and I have to say, these are not from NASA. This Jupiter one was UC Santa Cruz, and this was just some random guy that was looking through data and spotted this Einstein ring. I meant to bring in a wine glass to explain this, but this is more about, like, you know, weird gravity stuff. Let's zoom it on in here. There it is. This is when there's one thing that's massive and there's something else behind it, and the light gets bent around it. Sort of like if I held up like a wine glass. This is not a wine glass, it's just a cup. But imagine it was a wine glass and I did this and my face would look super weird all around it. That's an Einstein ring. Sean Kelly says, or Tom says, I think Jupiter's atmosphere can be really warm. Sean Kelly says, will Webb be looking at Uranus and Neptune? And also Sean asked, is brighter hotter? In some cases, with those Jupiter images, they were actually the caption that I was reading. Here, let's go back just real quick and talk about Jupiter again. It was talking about how those regions are higher elevations, which could be part of the reason that they're warmer. They're reflecting more sunlight. So anyway, how does amateur random guy find this really cool Einstein ring? Can you process images from James Webb yourself? Yes, you can. I know we have some astro imagers out there. How do you do it? There was actually a really interesting article on space.com about it. If you just Google, like, how do I process James Webb images myself? It will tell you that you're going to start at the MAST archives. It's like all the images from all the space telescopes. If you went to this link, which again is very easily Googleable, you go there, and at the very top left, there's like a search bar. So you say, like, I want to look for, I love M13. It's a globular cluster in Hercules. It's one of my favorite deep sky objects. So I would just type in M13. Then it's going to give me thousands of images from every space telescope image from all the space telescopes, and I can filter it down from that. And it will give me the raw data from James Webb if it has imaged M13 at this point. Then I can go through and do some different filtering and studying and figure out all that different stuff. So you too can get really cool images like that Jupiter image from UC Santa Cruz or that Einstein ring that random guy on Reddit posted. Okay, before I turn it over to Rocio, because I can't wait to hear, I just have to show you another just couple super amazing images. I almost cried when this one popped into my feed earlier this week. Oh gosh. Look at this image. This is called the Phantom Galaxy, and they call it that because it's notoriously difficult to actually find in your telescope because it is pretty faint. It's about 32 million light years away. And it's almost exactly like face on from Earth. So we have a really great view. And this, again, this is what we're seeing in infrared wavelengths, which lets us see right through to like the heart of that galaxy, which we have a harder time seeing in visible wavelengths. Here is an image that shows like 3 different things, right? When you look at it in optical wavelengths, this is what Hubble saw looking at this galaxy. Again, spectacular, breathtaking image. Here is what James Webb saw in infrared. Then they like combined them to make this super cool, really pretty image. I have to say I'm partial to just the Webb one in terms of the colors. You know, those colors are so cool. Also at much higher resolution. If you want to just come and enjoy this, I actually already scripted this into the planetarium. I have all this stuff in the planetarium already. You come to one of our shows, ask to see it, we'll show you. But I put this up full dome and then I make it slowly spin around you like you're spiraling through space in this beautiful galaxy.
Wow.
Just for fun.
Web
So
version,
there's, what's that?
Web version looks like one of those mathematical descending fractals, like that keeps going on forever and ever.
Yeah. I mean, I could stare at that all day.
I think that's what they're
I
called.
really could.
All right. Fantastic. You did good.
Okay. That's the end of what I have, and I'm thrilled to turn it over to Rocio, but if there are any final questions, now is a great time for that.
I have one.
Yeah.
In the
Thanks, Robert.
in the website, the URL you gave, it had the word client in there. Do you have to be a client or something or signed in?
You do not.
Okay.
No, I tried it myself. I like typed it in and I like pulled out all the things. I followed the instructions because I didn't want to like lead you down this path if you couldn't actually try it. I didn't like process the images. I don't have all that software. You can get it for free most of the time. So if that's something you're into, give it a try. Like Google how to do it. There are some tutorials. But then when you get something cool, please send it to me. I'll put it in the planetarium.
Okay, thank you.
Want to introduce your friend Rocio Kiman now?
Oh, Dr. Rocio Kiman, as we know, studies low mass stars. She has had a lot of outreach experience, both at the American Museum of Natural History and now at the smaller but far superior Santa Barbara Museum of Natural History. She's laughing because, of course, you know, who am I to say it's superior, but I guess I can. She is a fantastic interpreter, and I can't wait to hear what she says. I don't want to spend more time introducing. I just want to spend more time listening. So I'm turning it over.
Hello, Dr. Rocio.
That's so hard to follow, Krissie. That was an amazing presentation. Thank you. Well, hopefully you will have fun with what I have to say too. So thank you for having me here. I'm Rocio Kiman. I'm a postdoc, like people mentioned, at Caltech. I just started yesterday, so it's an interesting time. So I'm gonna go ahead and share my screen. Let's see. All right, is that working? Yep. All right. So I call these first findings. I'm just going to tell you a little bit about, kind of want to tell you what it's like to be a scientist in a JWST era. Because hopefully you all agree by now that JWST is amazing. Krissie showed us amazing pictures. We have this huge mirror with amazing precision instruments inside it in the middle of space, with a tennis court size sun shield just orbiting us, around us. It's with this huge team of people that worked for so many years to put JWST where it is now and doing the science that now is starting to do. And it's so amazing, all of these images that we are looking at. Then when I sit down and look at them for a little bit, it almost looks like science fiction. It's like we're looking at the universe this way, these crazy, amazing pictures that we astronomers as well as the general public love. But what we need to remember is that this is way far from science fiction. This is happening. JWST is real, it's there, it's taking data, and it's going to help us just revolutionize astronomy as we know it. Well, at least in the infrared, but it's doing a huge deal, as Hubble did in its own time. But so how do we do science with JWST? What does it mean to do science? I'm gonna make, well, this space is smaller. So as this is science, basically. This is myself in an observing run. And this is science. And this is science as well. So there is a huge crowd of scientists behind it, not only the amazing JWST team, but also the scientific community that is ready and anxious, waiting for the data to arrive and start analyzing, studying new objects and creating new knowledge, as we like to do. So how does everything start? So like everything, it starts with an idea, a topic that you're studying, that a scientist, an astronomer, or can come up with. And I wanted to talk a little bit more about what this means. So we have scientists that do research in a certain area, and in that area, suddenly they realize they did have JWST. So what does this mean? Let's imagine that you like to travel, right? So you want to go to a distant city, a village, maybe a small village. So you look it up in the map. Before internet, we would look at it in a map, maybe look at information in a book, try to look for the name of the village somewhere, try to look for information, what can we find, what can we do in this village? But there is a limited amount of questions that we can answer with this available information, instruments, like our books or maps, like a globe. So now let's put internet in the picture. Now you have this tool. Not only you can go and Google the name of the village, go and look what things there are in that small village that you wanted to see. You can actually go into Google Maps, put yourself in the village and just walk around the village. So there is a huge difference. Now you have this instrument that opens you so many more doors to answer questions that before you just couldn't do. And that's what JWST is doing for us. It's opening this huge door into the infrared, where now we can answer questions that we couldn't even possibly or either imagine, or it was too complicated to answer without JWST. So basically, we said we come up with a topic, a question that we want to answer that now we can answer with JWST. And we would select the objects that will help answer this question that we came up with. And we would look at the position in the sky and select that target. That target can be a star, an exoplanet, a brown dwarf, a galaxy, a lot of things in the universe. That's all of the things that, some of the things that JWST is going to be studying. And as Krissie mentioned already, JWST is orbiting us in this L2 point, so it's kind of outside of Earth, and it's going to be orbiting with us, the sun. So at different points during time, it can point to different places in the universe, basically. So that list of targets that we selected before that we needed to answer that question, the JWST team can decide to point to those targets and actually get the data that we need to the target that they selected before. But how does the JWST team decide where to point the telescope? We have this huge telescope again in space. We can point it wherever we want. Where do we point the telescope? For that, they did different programs. To look at all of the things that I'm going to show now are in this website that I copy there. So you can just go into your web browser and just put the website and you will find all of the programs that JWST has. So those programs are, for example, calibrations, right? They are doing certain observations to calibrate all of the instruments that JWST has. And prepare them for all of the science that is going to come after. Then we have the first images, those that Krissie was showing before. Those images were selected by the team as a way to show the observatory's capabilities and to just show what it's capable of doing. Then we have the early release science. So now we're getting into people actually using this data, because we remember that even though there's a lot of scientists, not a lot of people actually seen this data before. It's new. We don't know how to process it, how to analyze it. So we have this, the team came up with this early release science programs that is going to be a certain number of topics that are going to be investigated, certain objects that are going to be looked at to understand how the instruments and the modes of each instrument work. These were selected in 2017, so it's been a while that they selected these programs. Then we have the guaranteed time observation, the GTO programs. This is a part of the time of the telescope which is reserved for the members of the community, the team, that participated in the instruments and the telescope science, that they have also science that they want to do with the things that they build. So they get part of the time to decide what they want to do. And finally, but not least, we have the general observers, the GEO programs. This is open to the scientific community, and any scientist can put a proposal, select certain targets, come up with a scientific case, saying why those targets are important, and send that proposal to JWST. Those proposals are going to be studied by peers, so other scientists are going to read all the proposals, are going to review them, and they're going to rank them. And from those proposals, the ones that they're going to select the ones that are going to actually get observed by JWST. So I'm going to talk to you about some of this, not all of them, of course, some of the early release science that are just out of the oven, so very, very recent. And only one general observer program, which is one I'm going to be participating in to tell you what it's like. So this is, if you go into the early science programs, you get to see all these labels with the different topics that are being covered by this early science. Again, all of these topics are, it's a scientific, an object that is interesting to study its science, but also it's a very important object to understand how the instrument works and how to process the data, because this is going to be an example for the rest of the community. So going into one of them, this is an image that you might have seen. It's the first exoplanet image. It was submitted on August 31st, this paper. So 2 days ago, right, like I mentioned, right out of the oven. This is very new. And this was the first time JWST imaged an exoplanet. That means basically it took a picture. And this is this is a paper, the publication that came out with that result. You can see the title of the publication, and then below all of the authors, all of the people that contributed to that work. So we can see this is a huge team effort. There's a lot of people working on this data. And if you would like to go and see the paper, there's a link down there to get the PDF if you're interested in actually reading the scientific paper. So this exoplanet is HIP 65426P, and let's learn a bit more about it. Oops. So this is the image that NASA released, like a compilation of all of the different bands from JWST from 2 different instruments, the NIRCam and the mid-infrared. And what we can see here is the star, HIP 65426, that is hosting that exoplanet. We call it the same name of the star, P. That's how we name the planet. A lot of weird conventions. And as you can see in the zoom image, what is happening here is that they are testing one particular mode, that is the high contrast imaging, both from the near camera and the mirroring instrument. So what they are doing is using a coronagraph that's basically covering, like if you put like a paper covering, it's not a paper, of course, but it's covering the star. So covering the light from the star to be able to see the exoplanet. So if you see the white star over there, that's where the star should be, but it's actually covered, so we don't see the light coming from the star. It's like if you try to see a firefly right next to a lantern, it's going to be hard. You have to kind of cover the light from the lantern to actually be able to see what is around it. And we can see the little exoplanet over there. So like I mentioned, this is the first JWST image of an exoplanet, and it's the first image of an exoplanet beyond 5 microns. That means that goes into the infrared. That was the what Krissie was talking about, how JWST is important because it measures into the infrared. You can divide the infrared in different parts, like near infrared or mid infrared, and beyond 5 microns you get into the mid infrared, which we never had an image before. Then this object was selected, as I mentioned, to test the high contrast imaging mode, which is basically this of covering the star with the coronagraph and trying to see what is around the star. And they're using the near cam and the mirror. There are these two. This is a super Jupiter exoplanet. It has around 7 Jupiter masses. So it's bigger than Jupiter, the one that we know, and it's at a separation of 87 AU from the star. All of this can be measured from these images that they took. And what they realized analyzing this data is that JWST is performing 10 times better than expecting in the contrast limit. So it's doing much better dealing with the contrast than they were expecting, the contrast between the bright star and the exoplanet. That means that until now, we could only directly image, so take a picture of exoplanets that had more than 2 Jupiter masses. But now we expect to be able to see with JWST sub-Jupiters. That means exoplanets that are smaller than Jupiter, like a 0.3 Jupiter mass at a separation bigger than 100 AU, around the star as bright as this one, which is an A star, which is approximately 2 solar masses. And we could even see a Saturn, so a smaller Saturn, around an M dwarf, which is less bright, so that it's easier to see things around it because there's not so much contrast. Imagine that if you have like a bright light and a dimmer light, it's going to be easier to see around the dimmer light. This is the same thing happening with the M dwarf. So around a dimmer star, we would be able to see even smaller planets, even closer to the star. This is a 10 AU separation. And just as a reminder, 1 AU is the distance between the sun and the Earth, just as a comparison. So I know there's a lot of information, but if you want to take out something from this one of these first studies that people made, is that this high contrast imaging mode of JWST is so precise that we can image smaller exoplanets and closer to the host star. So this is what I was saying, that with this early release science program, we are starting to understand as a community what this instrument is capable of doing, how to use it, how to process the data. So these examples are just opening this door for everyone else to actually go and ask for their own data to do their own science. The second one that I want to mention is also a very recent paper. So it was submitted September 1st. This is yesterday. I just saw the images in Twitter, so everyone is super excited about this one. So it's the first brown dwarf for which we can get a spectrum from its full luminosity range. It's called BHS 1256b. Again, the B, it means that it's orbiting something else. In this case, it's a binary star. It's a binary M dwarf, and the brown dwarf is around it. And this brown dwarf has the particularity that it has a spectrum similar to a planet, to a giant planet. So I've been saying brown dwarf a lot, and I know that you mentioned it as a topic that hasn't come up a lot. So I'm gonna very quickly define very loosely what a brown dwarf is. You should definitely have a talk about brown dwarfs. They are amazing objects, very interesting. So if we have in this image, we have higher mass on this side and lower mass as we go to the right. So when we have more than around 0.1 solar masses, we have stars. We have objects that are massive enough to have enough pressure and temperature in their core to burn hydrogen. So once they start burning hydrogen, they get into the main sequence and they behave like a star. We know that it does, depending on its mass. If we cross a limited mass, there's not going to be enough material for the star to start burning, for the object to start burning hydrogen. So it can burn deuterium only, but after that, it's just going to cool down with time. It's a very hot object because after its formation, and then it's just going to cool down. Those are the brown dwarfs. And they can get to very cool temperatures where their atmosphere becomes extremely interesting. All of these molecules start to appear as you go to lower and lower temperatures, which makes them very interesting. In particular, because if you go to enough lower temperatures, these atmospheres start to behave like a planet. So if you go to lower and lower masses, you eventually get to what a planet is. But their atmospheres start to behave similarly earlier than that limit. And the brown dwarf is slightly easier to observe because the brown dwarf is much hotter than the planet, and it's easier to get a spectrum from that object, for example, study their atmosphere, and that's going to tell us something about the atmosphere of the planet, which, as it says there, it doesn't burn anything. So that is very quickly brown dwarfs. And going back to what people did was to select this brown dwarf, which is a widely separated brown dwarf from the binary that it's around it, that it's orbiting. So what we can do is get a spectrum of that brown dwarf without having a coronagraph on top of the binary star, because it's separated enough that we can see the companion. And this is the first time that we've seen such a precise spectrum covering the full luminosity range of the brown dwarf. As I was saying before, the brown dwarf forms and then cools down with time. So these are very hot objects and they emit in the infrared. This is exactly where JWST is. JWST is just looking at where the brown dwarf is emitting, and we can get a complete spectrum and study all of the details that we couldn't study before, or it was too hard to actually get the spectrum. So as I mentioned, this is the companion of a binary M dwarf, which is widely separated, and they are using near-spec and MIRI integral field photometry, so basically no coronagraph to get the spectrum. It has less than 20 Jupiter masses. It's a brown dwarf and has a planet-like spectrum. And with JWST, they got a spectrum from 1 to 20 microns at high resolution, which is basically the first time that we have been able to do that. what they found was signals of water, methane, carbon monoxide, carbon dioxide, sodium, and potassium. This is related to what Krissie was talking about before, how as the light goes across for a cloud, or in this case, the atmosphere of the object, part of the light is going to get absorbed. And in this case, there are molecules in the atmosphere that is going to absorb in a certain range or in a certain wavelength, and it's going to generate a shape in the spectrum. Then we can go and look for, once we take a spectrum, and try to understand what the atmosphere of this object is made of. And this is the first time that we were able to, for a planetary mass object, which is this case of this brown dwarf, detect silicate clouds. So that we directly, we were able to observe directly these silicate clouds, that they are there. So again, we're still with this early release science. So we are testing how the instruments work and what they can do. So we got the first highest fidelity spectrum to date of a planetary mass object. And we found for the first time the detected silicate clouds. I'm not checking the questions. I'm sorry.
Can I ask a question?
Yes, of course.
A brown dwarf is between a planet and a star.
In mass, yes.
Okay, but it seems like there's a thin line between, I believe you said there was a star that is a binary with a brown dwarf. Is that possible, to be a binary with something that's almost a planet but isn't a star?
Oh, yes. Yeah, there are systems like that. If there is a big difference between the mass of the star and the brown dwarf, like the star is very massive and then the brown dwarf is less massive, it's just going to look like the star is still and the brown dwarf is going around it. But if they are similar masses, yes, you will see them like orbiting like a binary star.
I see. Wonder where they draw the line. When does a planet go fast enough that it becomes a binary and it's not just one of many?
Oh, no, that depends on the mass of the companion. So you will the definition of a planet is not that it's orbiting a star.
Gotcha.
Is the size, the composition of how massive that planet is. The distinction between planet and brown dwarf is tricky.
And that's your specialty, Dr. Kiman, right?
Not exactly. I'm going to start working on this. It's not my specialty, but yeah, definitely tricky to distinguish between the two.
Okay.
I don't know if there are more questions. Oh, the deuterium fuses differently. You need less energy to actually fuse deuterium. And what does burning means? Yeah, sorry, good question. Burning, what I meant by burning is that it's taking two molecules of hydrogen colliding together because they are moving very fast in the interior of the star. They are colliding and forming helium. And in that transition, the star emits energy, and that avoids the star from collapsing into itself. So that generates the equilibrium of the star. That's what I mean by fusion, by burning.
So let me ask you a question.
Yeah.
When you showed the spectrum of the brown dwarf and you said over the full luminosity range, you're only looking at one object, right?
Yes.
Does that object change its luminosity over time?
Yes.
So you
over millions of years, right?
Okay, but during your measurement, what does it mean to measure it over a full luminosity range?
Good.
That
means the wavelength. So I'm covering all of the wavelengths that it's emitting in.
Yeah, I get it. Thank you.
Good question.
Good question.
Yeah.
All right. Incidentally, what does deuterium fuse into? Helium?
That's a good question. I'm not sure.
Okay, just curious. Wrap that question up. Didn't mean to take you off your track, Dr. Rocio. We see
No,
your.
I'm stopping because I was looking, it was accumulation of questions, but I can go back then. So just to keep going, I also don't want to go over time. I want to go back now to the other way of selecting targets for JWST, that are these general observer programs, which I mentioned, that is the scientific community puts proposals and selects objects that would be interesting to study and say why they are interesting to study, and some other scientists review those proposals and decide which ones are actually going to go into JWST. And you can see again all of the topics that are covered in these different proposals. If you go into this website, you can go and look at all of them and read what people are trying to study with JWST. I'm going to focus on one, the stellars and physics stellar types. And this is the proposal that I'm going to be working on. It's called Explaining the Diversity of Cold Worlds, and it was put by Jackie Parity, which is a researcher at the American Museum of Natural History. Actually, if you want an expert on brown dwarfs, this will be a great one to, Jackie is a great one to invite. She was my PhD advisor. She's amazing. And she came up with this project idea to use with JWST that I'm going to briefly talk to you about what we're going to be doing. So again, we have the brown dwarfs. This is a proposal for 12 brown dwarfs, and all of these brown dwarfs are cold enough that can help us understand Jupiter-like atmosphere. This is similar to what I was just telling you about. So what happens? We have this plot that is the color magnitude diagram. It's very common in astronomy. So we have brightness increasing up and temperature that increase to the left. We're astronomy conventions, that's how it works. And all of the points are measurements for different brown dwarfs. And the ones that have a black circle around it are the ones that are going to be observed in this proposal. And as you can see, when the stars are close to each other in this color magnitude diagram, that means that they are similar, they have similar properties. And what we are selecting here are outliers, are stars that deviate from that median. So there are physical reasons why they deviate from that median. And we want to understand what are those reasons why they deviate. Why we want to do that? If we look at the models, there are models that we can try to simulate one of these stars and see where it would be in this color magnitude diagram according to their physical properties. And if we plot the models on this plot, the models are all of these lines, and we see that they do not reproduce the observations at all. So what this means is that there is a lot of physics that is not going into the model to explain the position of the stars in the color magnitude of the brown dwarf, in this case, sorry, in the color magnitude diagram. So what we're going to do is get near spec high resolution spectra and mirror photometry to be able to understand the question that is in the orange box. So why are these objects outliers? So we're looking for evidence of unaccounted physics like cloud properties of the brown dwarf, metallicity, gravity, binarity, and chemistry. So we're trying to see if we can find any evidence of all of these properties in the spectrum, in the photometry, to try to understand these objects and try to see what physics we still don't understand from these objects that can then help the models to reproduce the data and us understand these objects better. So that's it. Thank you very much. And also, if at any point you have questions about JWST, they have a very cool website where with quick facts, and below that you can actually go and type a question about JWST, whatever you want. So, yep, thanks a lot.
You did good. Anybody have a question? Follow up.
I think she answered all my questions.
Yes, you did. We're going to have you back someday, Dr. Rocio, to talk more about brown dwarfs and your specialty and check up on your career. Krissie, thank you again very much. Did you have anything you wanted to add at the end, Krissie Cook?
I would love to give Tom Totten a shout out for being fantastic at covering that YouTube chat and getting the questions back and forth. We couldn't do it without you.
That's
Thank
true.
you, Tom. You're the man making it all come together. So great. And Rocio, fantastic job. Great talk.
Thank you for your talks, Krissie and Rocio. It was an excellent talk. Very, very entertaining, very information full.
Sean Kelly was with us the whole time, I think. He's our connection at City College, one of their astronomy professors. Real quickly, before you close us down, Dr. Jerry, it's hard to call you Dr. Wilson. President Wilson does have a ring to it, but it takes us back.
The Prez. Call me the Prez.
Next month, on the 7th of October, our speaker will be Dr. Claudio Campagnari, who is connected to the CERN particle accelerator thing. And he loves talking, and it said on his website, he was in charge out there of the physics department at UCSB. And he's out talking to everybody. He's going to talk to us. He looked forward to it. So we'll have him as our next speaker. And thank you. Don't get too hot, Mr. President. You want to gavel the meeting closed?